reviewing. Okay, so we've got this, and this is something we can kind of see in our mind's eye, right? We have this available to us inside of our brain, and this is going to help us be very, very proficient at solving some of these problems that we'll need to solve related to it. Okay, so some general comments. Because the amount of energy and so the frequency of an electromagnetic wave is what we're most concerned about, we usually display the various types of electromagnetic waves in order of increasing frequency. Okay, we have this general motion from lower left to upper right. Okay, and notice that the progression of frequencies in the chart above, you don't need to have detailed knowledge of values of frequencies. That's not necessary. However, wavelengths are slightly less annoying and easier to deal with mathematically. So we have to be able to visualize the spectrum in the order shown above, but realize that wavelengths get smaller when we do that. Also notice visible light's in the middle of the chart, and that's our reference point, right? Above this point, it's also more likely that electromagnetic radiation will have enough energy to damage biological tissues. With increasing energy and frequency, red light has the lowest energy, and frequencies just below this are infrared. Violet has the highest energy in visible light, right? And frequencies above that are ultraviolet. We remind ourselves of the colors, and 750 is red and 400 is violet. And then we have some terms here. If I just have a electromagnetic wave of one wavelength, that's called monochromatic light. Okay? If I have light of multiple wavelengths, and it doesn't have to be a continuous range of frequencies. It can be a frequency here, and then a frequency here, and then a frequency here. That's polychromatic light. And then if I combine all of those frequencies, I get white light. And then we remember that things with lower energy, radio waves and microwaves, have the lowest energy and the longest wavelengths. Well, it's not absolutely essential. It is helpful to have an idea that microwaves have wavelengths that range from about millimeters to hundreds of meters, and that should be centimeters, shouldn't it? Not decameters. Centimeters are hundreds of meters, right? 10 to the negative second is centimeters. Radio waves have lengths that are usually longer than meters. And then again, rays have the highest energy and shortest wavelengths. It is helpful to have an understanding that X-rays have wavelengths from nanometers to picometers. And remember we said 10 to the negative third is millimeters, 10 to the negative sixth is micrometers, 10 to the negative ninth is nanometers, 10 to the negative 12th is picometers, or PM. And then if we go to 10 to the negative 15th, that's femtometers. Okay? So X-rays range from nanometers to picometers, and then gamma rays have wavelengths that are shorter than picometers. And recognize this is a billionth of a meter. Okay? How much energy would I have to vibrate with a wavelength that's a billionth of a meter? Can you imagine that? Okay, so we need to be able to do some problems. The dental hygienist uses X-rays, wavelength, 1 angstrom. You might see this unit, an angstrom, designated by an A with a little circle over the top of it like that, is 10 to the negative 10th meters. Okay, so it's not a standard unit, but it was what we used to measure wavelengths in before we started measuring wavelengths in nanometers. Okay, so 10 to the negative 10th. So a wavelength of 1 times 10 to the negative 10th, and remember that is between nanometers and picometers, right? So that's consistent with what we know. Okay, so dental hygienists use x-rays at 1 times 10 to the negative 10th meters to take a series of dental radiographs while the patient listens to a radio station with a wavelength of 325 centimeters and looks out the window at the blue sky with a wavelength of 473 nanometers. What is the frequency in, and what did we say this unit was? S to the negative first, or 1 per second, 1 wave per second, right? That's what that means, 1 wave per second. The negative shouldn't be there. But that means it's 1 over seconds, right? 1 per second, and that's a hertz, right? Okay, what is the frequency of the electromagnetic radiation from each source? Assume that radiation travels at the speed of light, 3 times 10 to the 8th meters per second. Okay, and so I want to know what frequency is. And I know my basic relationship is the speed equals the wavelength times the frequency, right? And we talked about how we could remember that yesterday too, but it's really a pretty straightforward relationship, right? And so if I want the frequency, I'm going to isolate that by saying frequency equals C over lambda. What's new? C over lambda, right? Anyway, 3 times 10 to the negative, or 3 times 10 to the 8th meters per second. And in this first one, my wavelength, and we need to turn all of these things into meters, okay, so that we can cancel out the meters. 3 times 10 to the 8th meters per second divided by, in the first one, 1 times 10 to the negative 10th meters per wave. And recognize that if I do this, if I divide meters per second by meters per wave, that gives me waves per second, right? Which is what we want. Remember that when we divide by a fraction, that's the same thing as multiplying by the reciprocal. So if I multiply meters per second by waves per meter, meters cancel out and give me waves per second, which is what we want, right? That's what the frequency is, waves per second. Okay, so, and looking at this, remembering how to kind of predict what your answer is going to be. And we can do this one without a calculator, right? 3 divided by 1 is just 3, and 10 to the 8th divided by 10 to the negative 10th is 10 to the 18th, right? Because we say 8 minus negative 10. 8 minus negative 10 is the same thing as 8 plus 10. So we should get 3 times 10 to the 18th beats per second. Okay, now, that's a little bit inconsistent, isn't it? Oh, we're talking about frequency now, not wavelength. I was thinking wavelength for a second. It's like, well, 10 to the 18th is, but that's an enormous frequency. See, 10 to the 18th is quadrillion. This wave is moving up and down, or back and forth, a quadrillion times a second. How much energy would I need to wave a quadrillion times a second? A lot. Okay? And we can just do the same thing with the others. Equals C over lambda equals 3 times 10 to the 8th meters per second divided by, And so in meters, this would be how many meters? 325 centimeters is 3.25 meters, right?
Yeah.
Okay, so this is going to be about 1 times 10 to the 7th, because I'm dividing 10 to the 8th by 10 to the, well, actually 10 to the 0, so it's going to be about 10 to the 8th, isn't it? Anybody get that? Or so who's going to,
I got it.
what was it?
Big number. 9230769.2.31. So
I want it in exponential
yeah, I know.
scientific notation. 9.2 what?
Working on the scientific notation part.
You could set your calculator so that it automatically does that.
To the 7th?
10 to the 7th, 9.2,
Yeah,
okay. Okay, that's almost 10 to the 8th, right? Because 9's almost 10.
How do you do that? I don't know how you do that.
I think it's under mode and then. I don't know. Actually, so normal and then I think it's SCI.
Oh, yeah, that makes sense.
Sky, psi.
Yeah.
Okay, and then 3 times 10 to the 8th meters per second divided by, so nanometers is 10 to the 9th, okay? And so I've got 473 of them, so that's going to be 4.73 times 10 to the 7th meters. 4.73 times 10 to the 7th, 10 to the negative 7th meters, sorry. So my answer is going to be somewhere in the range of 10 to the negative, or 10 to the 15th. Or 1 times 10 to the 15th. 7.5 times 10 to the...
How did you get the 4.73? Oh, wait.
Okay, because it's 473 times 10 to the negative 9th,
Gotcha.
right? And so I just moved the decimal place 2 points to the left and said 10 to the negative 7th. Okay, so all of that stuff is stuff that you should be able to do in your head. That conversion from one type of part of a meter to another type of a part of a meter. So what's that?
6.3. Did you want 2 decimals or 1?
It doesn't matter.
Okay, 6.34 times 10 to the 7th.
It's not going to be 10 to the 7th.
I got to the 14th.
There we go.
I must have done something.
Did you read the 7th? You did?
Yeah, but when I did that, it was showing 10 to the 0.
Yeah, it wouldn't be 10 to the 7th. It would, so somehow you messed up.
I didn't include the times 10 to the negative 7th. That was my bad.
Okay. 6.3 times 10 to the 14th. So you can see all of the problems that you might run into on a calculator associated with this type of a problem, right?
Yeah, 6.34 to the 14th. There we go.
So you have to be able to at least estimate what.
Yeah, and that's the only way you're going to prevent yourself from making a mistake, right? So 8 minus negative 7 is the same thing as 8 plus 7, that's 15. And you should be within one number, one exponent of that. And if you're not, then you screwed up. Okay, so I have some other problems here that we're going to look at. And unfortunately, like I said, my printer did not want to print these. So let's, well, not my printer, but the school printer didn't print them. I tried 3 times. So what I'm going to do is go down there and find 3 copies of, or 3 times 7 of these. Let's cover my answers here. Yeah, I'm going to have about 20 of these.
What would you use for units for this?
Huh?
What would you use for units
In what?
for the answer? Or do you just have the answer?
In this question?
No, the one that.
Oh, meters, or I'm sorry, meters, frequency, it's meters, waves per second, right? Hertz. I'll say, so for all of them, the frequency's in hertz, right? HZs. Or you could say this unit would be s to the negative ones too, and that's the same thing. Okay, so I want to cover up answers here. Okay. So, when ignited, a uranium compound burns with a green flame. The wavelength of light given off by this flame is shorter than that of which of these types of light? So I've got green light. It's in between red and violet, right? Okay. And my wavelengths increase going to the left, decrease going to the right. So
What's higher energy?
we don't even need to worry about energy here.
Yeah, well, that's just how I'm thinking about it, because I've
It's gonna be
never
infrared.
energy.
Huh?
It's going to be infrared.
Okay, so it's going to be shorter than that of infrared. Everything else is of a higher wavelength than visible light, right? This is higher, well, violet light is higher than green light. Gamma rays are higher than visible light. Ultraviolet's higher than visible light. So the green light, which sits right in the middle of red and violet right here, is going to have to be shorter wavelength than, what happened? Oh, come on, why are you doing this to me? It's going to have to be shorter wavelength than that 750, right? Which means to the right of, not to the left of. So you can see how your understanding of the electromagnetic spectrum, if it's really intuitive, it can help you solve these really quickly. And you can see that I've got answers here. You should be able to figure that out within about 15 seconds. Which form of electromagnetic radiation has wavelengths that are shorter than those of UV light?
Gamma rays.
Gamma rays, right? Everything else is longer than actually, I'll just do this. Okay, which of the following frequencies corresponds to light with the longest wavelength? Light with the longest wavelength means with the lowest frequency, right? So which one of those is the lowest frequency?
What? E? No. That's not.
And remember, that means hertz, right? That's frequency. Hertz is, which is, yeah, it's D, right? That's the shortest, or that's the lowest frequency.
What's the difference between the 1 and the negative 1?
The negative one?
Yeah.
That always means the reciprocal of. If it's 10 to the negative 1, or if it's s to the negative 1, that's something per second. If I had s to the 1, that would mean seconds. So if I use it with units, okay, if I use an exponent with units, I'll only use a 1 or a negative 1. And you'll never use a 1 because you're just going to say seconds, right? Okay, but if I said meters to the negative 1, that would be the same thing as 1 over meters. Okay, something per meter. Okay, you can also read that as per, 1 per meter. Okay,
So which is the correct answer again?
it's going to be D, because it's got the lowest frequency, right?
Yeah.
That means the longest wavelength. Okay? So when you think frequency versus wavelength, if you've got something that's asking for the longest wavelength, you immediately think the lowest frequency. If you are asking for the shortest wavelength, you're thinking highest frequency, right? Because they're inverse. Okay?
I didn't see before that they all have negative in front of the ones.
Uh-huh.
They were kind of blocked out. I see it now, but for a second I didn't realize it, and that threw me off. I was going to say D originally, but then I noticed that from my point of view it didn't have a negative in front of it, so then I kind of...
That's fine.
You second guessed yourself.
Well, yeah, because it wouldn't make sense because then it would have been answering as that's how many seconds it was because
Yeah.
I didn't see.
Yeah.
That's right. This means waves per second.
Yeah, and I just hadn't seen the negative sign. It looked like it
Okay.
didn't have it.
That's all right. Which of the following are incorrectly paired? And there is a negative in front of that one. Which?
It's A, isn't it?
Yeah, it's A. Speed of light should be C.
Oh, yeah.
So wavelength is lambda, hertz is waves per second, frequency is Greek letter nu, right? Okay, pair the following waves with the corresponding range of wavelengths. If you were to get something like this, you would immediately go to visible light because you know what the wavelength range for visible light is, right? Which is that? That's F, right? Okay,
It doesn't have a bunch of tens in it.
so F is going to be that. You also know that radio waves are going to be the longest or the shortest?
Longest wavelength.
They're going to be the longest wavelength. So I'm going to look for something that's got meters in it, because radio waves are going to be meters. Okay, what's big capital M mean? That's mega. That's the word mega. So like megabytes, this is megameters, and that means million. So this is a decimeter and so B is going to be radio waves. Okay, and if you wanted to go to the shortest one, picometers to nanometers. Oh, less than picometers is going to be gamma rays, right? And then picometers to nanometers is going to be X-rays.
Which would mean that G is ultraviolet, right?
Uh-huh.
It's also nanometers.
Yep. And then infrared is going to be
Infrared.
micrometers to millimeters. So A, and microwaves would be D. Okay, is this making sense?
Yep. Yes.
Okay, and again, you can see how just having that intuitive sense of things will allow you to figure these things out pretty quickly. One last one here. When strontium salt is ignited, it burns with a red flame. The frequency of light given off by this is less than, okay, now we're talking frequency, so red light's going to be at the left end, right? And so it's going to be less than everything to the right of that.
So infrared. So
Well, no,
less
this is like one of the multiple
Yep,
answers ones.
yep.
But it's infrared.
Okay, so remember again, as far as frequency goes, this is going to be shorter than everything to the right of that.
So D.
Right?
145.
Doesn't the frequency go up though when you go that way?
Yeah, it does. So this is going to be less than, the red flame is going to be less than everything to the right.
So those aren't worth it.
So it's going to be 1, right? Blue light's up here somewhere, okay? Roy G. Biv, okay? Ultraviolet's up here,
So it'd be,
and X-rays are over here as well. So 1, 3, and 5.
so be.
Yep.
Got it.
Okay? You have to read these really carefully.
Yeah.
Otherwise, you're going to make a silly mistake. Okay. So, answering these kinds of questions was what the last lecture was all about. Okay? So you will see at least a couple of those kinds of questions on the test. And part of the reason for the reason we think this is so important is because this type of understanding is what led us to understand how the structure of the atom works. So that's why we pay so much attention to it. Okay, so the nature of matter. We need to understand the nature of matter. Prior to the late 1800s, all that we knew led us to the idea that matter was made of particles. Okay? That's all we really knew. Before the late 1800s, we knew that all matter was made of atoms or other particles that were made up of atoms. And we understood that because of the kinetic molecular theory, and we understood, Dalton synthesized all of this in the early 1800s and said things are made up of atoms, and if we interact these atoms together, we get conservation of matter. And so the atomic theory was pretty well entrenched by then, but we didn't know anything about the structure of the atom. We just knew that it was a particle. Okay? And we also knew that if what we knew from physics, we knew that if we added energy to particles, it would increase their motion. And if motion of particles decreased, energy was lost from the particles. We understood that from classical physics. We thought that if we added energy to these particles, they would speed up. And if we took away energy from those particles, they would slow down. Okay? But when we thought about that, we considered energy to be something very different from mass or from a particle. We thought energy was something that was very different than matter itself. They had distinctly different properties. Matter was made of particles that had mass and a definite position, and they moved with a certain motion through space. And we thought that energy was massless, and it traveled in electromagnetic waves, and we couldn't really locate it in space. Okay, so you can see how we would consider matter and energy to be completely separate things. So we also said that the matter in all objects is constantly absorbing and radiating electromagnetic energy. Because these particles are constantly smacking up against each other, they're constantly exchanging energy with each other, right? I smack this particle and I give this particle more energy, and this particle loses energy, so this particle that lost energy might radiate an electromagnetic wave because it lost energy. But we really didn't know why it lost that energy. But we assumed that all of the energy that objects radiated into the world around us was based simply on changes of motion of the atoms, right? That's all we understood. We understood that if I add energy to a particle, it speeds up. If I take energy away from a particle, it slows down. We did not understand that if I add energy to a particle, it might actually change the nature of the particle itself. Okay? We just thought it was going to speed the particle up or slow it down. We didn't know anything about if I add energy to an atom, it's going to increase the energy state of the atom itself. It's going to change not only the kinetic energy of the particle, it's going to change the potential energy of the particle by causing electrons to raise or lower to or from a higher energy state. We didn't know that. We assumed that some relationship would be developed between the change in the amount of motion of particles and the amount of energy that released. And we assumed that it would be continuous because that's all we know. If I push something a certain amount, it will increase its energy by a certain amount. If I add an infinitely smaller amount of energy, it will increase its motion by an infinitely smaller amount. We thought that the energy that we could add or take away from something was continuous. Okay? But then we hit an obstacle. In the late 1800s, we started investigating something called black body radiation. Okay? And a lot of this theory is beyond the scope of, or at least the mathematics that explain it, is beyond the scope of the AP class, but you have to sort of have this at least vague understanding of the concept. And that's all I'm going to ask, is that you have this vague understanding of this concept. All objects are constantly absorbing and emitting electromagnetic radiation. In general, we can't see this because its frequency is not in the visible light range, right? You can't tell that I'm radiating heat, right? Your eyes can't see infrared radiation. But if I got an infrared camera, you've seen how infrared cameras work. Now, be aware that a higher temperature doesn't really look red, okay? We add the red color into it just because that's what the way our mind thinks. The hotter something is, we think the redder it should be, right? Yeah.
Are there animals that can see infrared?
Yes, there are. Snakes can see infrared. Okay? Now, we usually talk about it when we talk about it in like a zoology class, that they can sense heat. Okay? We can sense heat too. Our skin has temperature receptors, and we can receive that. But their receptors are receiving electromagnetic radiation. They can actually sense the infrared waves. And there are also insects that can actually see in the ultraviolet range.
Are there a few birds that can see ultraviolet?
I'm not sure. I don't know.
So, just out of curiosity, what does that mean? Because, like, obviously, if a snake can see infrared, it can sense prey, but, like, how do things emit ultraviolet? Like, how do things emit ultraviolet, and what does it mean?
Okay, so, again, and obviously it's going to be a little bit more complicated than this, but, and this is a really hard concept.
Well, mostly I just mean, is it like for detection purposes, like it would be for a snake to help hunt?
Oh, yeah. Why? Yeah, that's the sole purpose for that, so that they can find prey. Yeah, I mean, they can see too. They don't just, but their sight's not all that great, but they have this infrared ability. Okay, so never mind.
I wonder what infrared looks like.
It would be cool, wouldn't it? It would be cool to be able to sense that, but it wouldn't really be a color. And anything that we call a visible color is something that's artificial, right? The only reason that we say that something is red is because that's the name we gave that appearance that our brain perceives. And what's red to you is going to be a little bit different than what's red to me.
I mean, when I think about all the colors that I can't see, I just feel so colorblind.
Yeah. Yeah. Well, and we probably shouldn't refer to things like ultraviolet and infrared as colors, because they're not really colors. That's an artificial concept, right? Yeah. That's just we should probably think about them just in terms of there are certain amounts of energy. But that's something that you could stay up late at night talking to your college classmates about, the philosophy of all of that.
Yeah, because like if my orange is a little bit different than your orange, in theory, depending on how different they are, like we could all have the same favorite color, just we have,
They're just
like it's a different name
Yeah.
for each person. Just the actual color, if you were to fit in their shoes, would be the same color,
Yeah.
like or
one man's red is another's orange.
Yeah, that's the thing.
Exactly. Okay, but this is way too philosophical for this class.
No, I just think it's.
So, in general, we can't see this radiation because the frequency is not in the visible light range. It's mostly infrared. However, you're also aware that if we heat some materials, if they don't combust, if I take a big chunk of iron and I start to heat it up, it's going to start to glow, right? This is because the increased temperature causes the material to emit electromagnetic radiation in the visible light spectrum. Okay? Normally, a chunk of iron sitting on my desk here is emitting infrared radiation. We can't see that. Okay? And in fact, at room temperature here, it would probably be cold enough that even an infrared camera is not going to really see it, quote unquote. But as we heat it up, it's going to start to emit electromagnetic radiation at higher and higher and higher energies. And again, it's because as those particles start to smack into each other at greater forces, when one of those particles loses its radiation or it loses its energy, it's going to be at a high enough energy that that energy is lost that we actually start to see that reddish color. So the first thing that we start to see when something starts to glow is going to be that reddish color, right? Because that's what's at the lowest energy end of the visible light spectrum. Okay? The greater the temperature, though, the further into the light spectrum we get. We go into the orange and then to the yellow, and then we actually will get into a point where we start to see all of these colors being emitted, and when all those colors are emitted, we see white light. And then it will even get to a higher level where we'll start to see that it's glowing a bluish color. Okay? And this is consistent enough that we can actually determine the temperature of the glowing material by the color of it. And this is how we know what the temperature of stars are. Okay? Consider the color of stars or of lava flows. Lava flows that are burning at a higher temperature are more yellowish or orangish color. Lava flows that are more lower temperature are more of a reddish color. Okay? Now, this type of radiation where frequencies of radiation emitted depend on the temperature is called black body radiation. Okay? The type of radiation where the frequencies of radiation emitted depend on the temperature is called black body radiation. If you go into chemistry, physical chemistry, as a junior or senior in college, you'll have to understand the mathematics behind this. All we need to know is that that's what this is called. Okay? The origin of this term is beyond the scope of this class, but the concept is something that I need you to understand. We call this type of radiation black body radiation. Okay? For these materials, we can measure the power of the energy that is emitted at each wavelength. And remember, we talked about that idea. When we talk about electromagnetic radiation, we'll oftentimes talk about the power, how many joules per second of energy are emitted at each wavelength. Okay? Now, again, this is going to be something that you don't need to understand in order to understand the consequences of this. Okay? So if we plot the power emitted at each wavelength, we get what your textbook calls a radiation profile. And they did not actually bother to give you a picture of that in your book, so I gave you a picture of what this looks like. But all this really is saying if I have this much power being emitted, and that's all you need to know about this, if I have this much power being emitted, okay, if I have this much power being emitted per wavelength, that's going to change depending on the temperature. Okay, so if I'm at 3,000 degrees Kelvin, which would be about 2,700 degrees Celsius, right? If I'm at about 3,000 degrees Kelvin, I'll just barely start to see some of this reddish glow. Okay, so if I heat my chunk of iron up to about 3,000 degrees Kelvin, I'll have a really nice red glow here. If I heat it up to 4,000 degrees Kelvin, I'll still have a lot of red, but I'll also have some orange and yellow and green and blue mixed in. So I'll be heating this up to more of a white hot temperature. If I heat this up to 5,000 degrees Kelvin, I will start to see a lot more of this bluish color. So I'll have a bluish tint to this, and I'll even get some into the ultraviolet range here. Okay, so all this chart is showing is that if I heat this object that's not going to react with the atmosphere because I've heated it so much, right? A chunk of iron is not going to react with the atmosphere just because I heat it up. Well, it will to a little degree, but it'll still glow. It's just showing that the higher the temperature I heat it to, the more of the violet end of the spectrum I'll see. That's all this is saying. Okay? Now, the details of this are beyond an AP chemistry class, but at that time, classical physics predicted that the amount of power radiated at a given temperature should increase at shorter and shorter wavelengths. Okay? The power should increase at shorter and shorter wavelengths. They thought that what we should see as far as wavelengths of light goes should just increase indefinitely. That's what classical physics predicted. And again, you don't need to know why it predicted that or anything. Just understand that classical physics predicted something other than what we saw. The actual radiation profile showed that the power emitted only increased to a certain wavelength, right here, but then at shorter wavelengths, the amount of power that was released decreased again. Okay? Again, you don't need to know these details. You just need to understand that what classical physics predicted was different than what we observed. Classical physics only considers the motion of particles that we can actually see. Okay? Classical physics doesn't consider what happens at the level of an atom. And what's going on here was occurring at the level of the atom, not what classical physics could see. But we didn't understand that atoms were anything other than just particles. We didn't know about electrons yet. We didn't know about protons yet. We didn't know about neutrons yet. So the actual radiation profile showed that the power emitted was different than what classical physics predicted. And no one can figure out a way to mathematically model this relationship. Enough of you are in calculus to know that we can find mathematical equations to model almost any curve we want to on a graph. Okay? I can find a mathematical statement that describes almost any curve I want to on a graph, but nobody could figure it out. Nobody could figure out a way to model this mathematically. Okay? Because they assumed that the loss of radiation, the radiation that was being emitted, was related to the fact that the particle motion slowed down when it lost the energy. They didn't know that something happened inside of the atom when it lost that energy. Yes, some of that energy that was lost resulted in the particle slowing down, but some of that energy lost also related to the fact that the electrons were dropping to lower energy levels inside the atom, and they did not know that. Now, you might think that that wouldn't make that much of a difference, right? So what? I've got an electron dropping from here to here. If I'm just talking about one atom, no big deal. But remember, in this volume of matter, we're not talking about just a few atoms. We're talking about 10 to the 23rd atoms or 10 to the 50th atoms. And if you have 10 to the 23rd atoms all losing energy at the same time, that's going to result in a pretty significant emission of energy. Okay? So it is just a little bit more than just one or two atoms that are losing this. And they didn't realize that all of these atoms were losing this potential energy by electrons dropping from a higher energy level to a lower energy level. And that made all the difference. Finally, in 1901, German physicist Max Planck developed a formula that perfectly described the radiation profile for black body radiation at particular temperatures. Your book states that Planck could only account for those observations only by postulating that energy can only be gained or lost in whole number multiples of the quantity h, and then again, this is not a v, this is the Greek letter nu, h times the frequency, where h is a constant called Planck's constant. Okay? Now, it's a very small constant, and multiplied by our frequencies, it's still a number with a large negative exponent. But that's just for one atom. But that's not the point. The point here is that this meant that energy could not be changed by just any amount. Okay? I can't change energy from here to here, or from here to here, or from here to here. I can only lose energy by this amount, or I can only gain energy by this amount. All of these other amounts in here are not allowed. Okay? That's what this meant. Okay? Energy can only be gained or lost in whole number multiples of this quantity. Okay? I can only lose energy from here to here. I can't lose energy from here to here, or from here to here, or from here to here. The loss of energy is not continuous. It's incremental. It's quantized. And that freaked everybody out. Nobody believed it because they all had their mindset on, when I lose energy from a particle, it just slows down. Okay? They didn't know that it also could result from an electron dropping from one level to another level. Okay? Now, this is important for a lot of reasons, but one of the things that really freaked people out was this meant that energy cannot be changed by just any amount. It can only be changed by certain multiples of the frequency of the energy that was emitted, and this implied that waves had properties of particles. Now, you would not expect the transfer of individual packets or quanta of energy unless the transfer occurred through something that has a particle nature. Okay, let's say that again. You would not expect the transfer of an individual packet of energy. If I drop from here to here in my energy, I wouldn't expect the transfer of that energy to be an individual packet of energy or quantum of energy unless this occurred through something that had a particle nature of a specific size. And what we're going to ultimately say is that this packet of energy that isn't a particle, but it is a particle, is a photon. Okay, so you've heard of photons of energy before, but a photon is a massless thing. It has no mass. Yeah?
Can I go to the bathroom?
Sure. It has no mass. Now, Planck's equation described the mathematical way to find the amount of power radiated by a black body at a certain temperature and wavelength. But we're more interested in the actual amount of energy itself, just the joules. We're not interested in the power that was transformed or that was released. We're interested in just how much energy, period, is released. And his formula allows us to do this as well. Planck's results suggested that energy can only be transferred as packets of energy that we call a quantum. And each quantum of energy transferred had the energy equal to Planck's constant times the frequency. So, if I have a wave, an electromagnetic wave, I can figure out how much energy is in that wave, and don't even think about trying to figure out where in this wave the photon is. Okay, that'll just drive you nuts. Don't worry about it, it's not important. But this wave is going to deliver a photon or a packet of energy. It's not going to deliver a little bit of energy from this part, and a little bit of energy from this part, and a little bit of energy from this part. When the wave smacks something, it will deliver a photon of energy to whatever it hits, unless it passes through it and doesn't deliver its energy. Remember, this wave is not going to transfer its energy unless it hits something that can be raised, an electron can be raised by that certain amount. If it hits something where that amount of energy is not allowed, it'll just pass on through it. It won't do anything. But we have lots of targets, so it's not as dire as it sounds. Anyway, the amount of energy is going to be Planck's constant, okay, that large negative number, 6.626 times 10 to the negative 34th, times whatever the frequency is. And since we know that the frequency is also the same thing as the speed of light divided by the wavelength, we can use the wavelength in this equation as well. So the amount of energy that's going to be transferred by this electromagnetic wave is going to be Planck's constant times whatever the frequency is. Okay, and we'll figure that out here in just a second. Einstein formalized the idea that electromagnetic energy, while having features of a wave, also had a particle nature. He was the one that took Planck's idea and said this. He was the one that coined the term photon. Okay, and he said that this wave has a particle nature to it, that it's very difficult to understand, a massless particle, and each with the amount of energy that Planck had counted. So he says the energy of a photon is the same thing here. Planck's constant times frequency. So, to put this in action, the blue color in fireworks is often achieved by heating copper chloride to about 1200 degrees Celsius. Then the compound emits blue light having a wavelength of 450 nanometers. What is the increment of energy, in other words, the quantum that is emitted at this wavelength? So all we have to do is say energy equals Planck's constant times the frequency, but we don't have the frequency, so we're going to say Planck's constant times c divided by the wavelength equals 6.626 times 10 to the negative 34th joules seconds. And don't worry, you don't have to memorize that. They'll give you that. And you'll almost certainly see a problem asking you to do this. Times 3 times 10 to the 8th meters per second divided by 450 nanometers, and that's going to be 4.50 times 10 to the negative 7th meters. Okay, recognize that the meters are going to cancel out. This per second is going to end up being in the denominator, and that will cancel out seconds. And that will leave us with joules, which is what we want. And I'm going to be multiplying 10 to the negative 34th times about 10 to the 15th, right? So my answer should be somewhere around 10 to the negative 19th.
I got 4.42 times 10 to the negative 19.
Okay. See how easy that is? 4.42 times 10 to the negative 19th joules. And again, this seems like a ridiculously small amount of energy. Oh my goodness. But if I have 10 to the 23rd particles that are doing that, right? This is the range of Avogadro's number, about a mole of particles doing this. Well, all of a sudden, I have 1,000 joules of energy being released there, right? 10 to the 23rd versus 10 to the negative 19th, that's going to end up with a value of about 10 to the 3rd or 10 to the 4th, 1,000 to 10,000 joules of energy. Okay? So then it doesn't seem so ridiculous, does it?
Because that's just one mole of whatever it is.
Yep.
And that's still a relatively small.
It is still a relatively small amount.
Like the mole itself. And so if you get like a handful
Although,
size,
yeah. Although a mole of copper chloride is going to be in the range of 150 grams per mole. So 150 grams is a reasonably sizable amount of copper chloride. But you're absolutely right. It's still not an enormous amount of material. Okay? So there's tremendous energy that's released in a lot of these reactions. And it's because of these potential energy changes that are going to occur when I interact with something else.
well, it makes sense too, because fireworks are really loud, so there's a lot of sound energy, and then it makes light.
A lot of light, and you don't want to hold it in your hands when it explodes, right?
Yeah.
Obviously.
Well, you certain does.
Or at least certain amputation.
Yeah.
Well, it depends how powerful
Sure.
the firework is.
Yeah, a firecracker's probably not going to mortally injure you, but
Just, there's little poppets.
an M60 could pretty much damage you.
I'm like, there's the little poppets that like people
Yeah.
pop between their fingers, so
Yeah, just a little spark of energy.
And then you have like really big ones that are really loud.
they hear 5 miles away.
Yeah, those are the cool ones.
Is this making any sense at all?
Yeah,
Yeah.
actually,
Starting
makes
to,
a lot
yeah.
of sense.
I am
Okay.
confused about the symbol it's supposed to be.
Which symbol?
By the -7.
Yeah.
Oh, that's meters. And I crossed it out because it canceled.
Oh, gotcha.
Yeah, I was confused.
It stands for the Marshall unit.
Marshall unit.
Wasn't there a different unit that you wanted to Marshall?
There's always some unit that I'm wanting to call marshals. It changes depending on the day and the circumstances.
So there's no one particular unit.
No, just whatever strikes my fancy is, hey, it would be nice to have something named after me. Then it's like, I'm just this teacher at Summit Academy High School. I don't need anything named after me. Well, it's enough just to be able to teach you amazing students.
Before being a teacher, though, you were a pathologist.
Yeah. I consider being a teacher more important than being a pathologist.
I mean,
Especially because you never know if one of your students might go on to discover something, name
Absolutely.
it after themselves, discover something else, and be like, Marshall.
Sure, that's entirely possible.
It's not very.
it's
But
possible.
you never know.
Possible, unlikely, but possible.
Yeah. Never say never,
Yeah.
unless there's a good reason to.
Unless there's a good reason.
Never say never, unless you need to say never, and then you can say never.
One student that I taught here my first year at Summit graduated not too long ago from Caltech,
Dang.
and he's a world famous theoretical physicist now.
Right.
Not necessarily because of anything I taught him, but
That's still cool, though.
yeah. But it's all relative, right? We're all, we all have our strengths and our importance to society. And no one's more important than anyone else. But I do for my wife. She goes, you used to be a doctor, now you're just a teacher. It's like, what?
But you're still Dr. Marshall.
Yeah.
Correct anyone whenever they call you Mr. Marshall, so.
It depends on whether or not they're pissing me off. If they happen to be irritating me at the time, I'll say that's Dr. Marshall. But I don't usually.
If it's one of your more tolerable students, you'll just let it slide.
Yep. Well, and it's not really that important.
I mean, it is your titles. So.
It is, but it's just my ego. So it's not an important thing. Unless they're pissing me off.
Yeah, the other doctor I know, I don't refer to him as doctor, I refer to him as dad, so.
Yeah, okay. That's funny. Yes, take care. See you guys.
Forgot we have presentation. I'll be back.